Let's walk through an example where we're going to use Euler's method to approximate the solution of the initial value problem, dy dx is equal to 2x, and y of 1 is equal to 1, at x is equal to 1.5, using a step size h is equal to 0.1. I chose this problem to use as an example because we know the solution to this differential equation. The exact solution is y is equal to x squared. Knowing this will help us determine how accurate our approximate solution is. The formula that we're going to use is y sub n plus 1 is equal to y sub n plus our step size h times f of x n y n. The first thing that you want to do when you're solving one of these problems is rewrite this formula in terms of the equation that we've been given. So we're going to start by writing down what f of xy is equal to. F of xy, for the example that we've been given, is just f of x, and it is the right-hand side, which is equal to 2x. It's always whatever the derivative is equal to. We can then say that f of x sub n is equal to 2xn. Let's now plug this into our formula. Our formula is y sub n plus 1 is equal to y sub n plus h times f of xn yn. Now let's plug in what f is. So we have y sub n plus 1 is equal to y sub n plus h, which in our problem is 0.1, times our function, which was 2x sub n. This gives us the formula y sub n plus 1 is equal to y sub n plus 0.2 x sub n. Writing this ahead of time just makes things a lot easier, so you don't have to go through that computation every time. Let's now look at this table down here on the left and fill in what we need to find. You're always going to start with n is equal to 0, and we can find x0 and y0 by looking back up here at our initial condition. Our initial condition tells us that x0 is equal to 1 and y0 is equal to 1. So we can put that into our chart. We'll fill out what the exact numbers are when we get done with our problem. We want to find an approximate solution at x is equal to 1.5, and our step size is 0.1. So x is going to be 1.1, 1.2, and then 1.3, 1.4, and 1.5. We're just adding our step size onto each value of x. We started with n is equal to 0, so then n is going to be 1, 2, 3, 4, and 5. Now we have to start computing what our values of y are. Let's start by saying that y0 is equal to 1, and let's make a note that x0 is also equal to 1, because we're going to need that. y1, looking over here up at the right at our formula, is going to be y0 plus 0.2 times x0. So this is 1 plus 0.2 times 1, and this gives us a value of 1.2. Let's go back up to our table and let's put that in. y1 is equal to 1.2. Now let's compute y2. It is equal to y1 plus 0.2 x1. y1 we just found was 1.2, and then we add 0.2. x1 is up in our table, and it is equal to 1.1. And this gives us a value of 1.42. And let's put that up here into our chart. Now we're going to compute y3. It is equal to y2 plus 0.2 times x2. y2 was 1.42. And then we multiply 0.2 times x2, which is 1.2. And we get a value of 1.66. Let's now compute y4. I'm not going to write down the formula because I think we already know what the pattern's going to be. y3 is our previous solution, 1.66, and then we add on 0.2 times our next x value, which is 1.3, and we get an answer of 1.92. Let's do it once more. y5 is equal to 1.92 plus 0.2 times 1.4, and this gives us a value of 2.2. Let's now put these values back up into our chart. We have 1.66, 1.92, and 2.2. We can now write down what our approximate solution is. We can say y at 1.5 is approximately 2.2. Let's now go back up to our table and put in the exact value, and then we can see how accurate the solution is. Our exact solution was y is equal to x squared. So when n is equal to 0, our exact solution is 1 squared, which is 1, and then we have 1.1 squared, which is 1.21, and then we get the rest of the values. We're just squaring what xn is. Going back to our approximate solution, we can compare this to our exact solution, which is equal to 2.25. So we can say that the absolute error is going to be our exact solution, 2.25, minus our approximate solution. And we have an absolute error of 0.05. And let's make a note, this is when our step size is 0.1. If we would have used a smaller step size, say h is equal to 0.01, we would have found that y at 1.5 is approximately 2.245. You have to do lots and lots of computations to get to this answer. The absolute error for this one would be 2.25 minus 2.245, which is equal to 0.005. And let's just mark this. This is h is equal to 0.01. You can see from this that if you used a smaller step size, your error is going to be much smaller. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.